Welcome back to the deep dive. Today we are tackling a big one. Large language models, LLMs.
Yep.
They power everything from chatbots to the tools that write code for us, and they can feel, well, a bit like magic.
They really can.
But they're not. They're built on some fascinatingly simple principles. And that's our goal today, to really peel back the layers and understand the nuts and bolts.
And the most important starting point, I think, for anyone listening is to realize that this whole thing, it all rests on one simple act.
Okay.
Predicting what comes next.
That's it.
That's it. If I start a sentence like, the cat sat on the
Your brain just automatically knows what's likely to follow.
mat or chair.
Something like that.
Exactly. An LLM is just a huge, incredibly sophisticated system doing that exact same calculation, but just on a colossal scale.
It's a next word predictor, just taken to the absolute extreme. So our mission today is to unpack that. We're going to look at the massive data that gives it its worldview, the four critical training stages that turn it from just a text generator into a helpful assistant, and then the controls, like temperature, that let us shape what it actually says. Okay, let's get into it. If an LLM is all about prediction, it can't be processing language like we do. So what's the smallest piece it's looking at?
It looks at something called a token.
A token.
Yeah, you can think of them as the LLM's building blocks for language. A token might be a whole word, like run, or just part of a word, maybe like the ing in running. Sometimes it's just punctuation.
So it's not letters, and it's not always words. It's something in between.
It's whatever is most efficient. The model looks at all the tokens you've given it in your prompt.
At the context.
The context, yes. And then it calculates the probability for every possible next token. And then it picks one.
So wait, whether I ask it to summarize a legal document or write a Python script, it's all just one token at a time. That almost feels too simple.
It does feel simple, but the cumulative effect is what's so powerful. Everything it does emerges from that one simple step, repeated over and over, based on the millions of patterns it learned from its training data.
And that data is just immense, right?
Immense is an understatement. We're talking billions, sometimes trillions of words from books, scientific papers, conversations from the web, code, basically a huge chunk of human knowledge digitized.
Okay, so let's talk about the engine that makes sense of all that data. We always hear the term transformer. What is that architecture? Why was it such a big deal?
So formally, an LLM is a transformer-based neural network. The reason transformer was such a breakthrough, this was back in 2017, is that it solved a huge problem older models had with long-term context.
Right, they would just sort of forget what happened at the start of a long paragraph.
Exactly. It was like trying to hold water in a leaky bucket. The context just drained away as it read word by word.
So what does the transformer do differently?
It uses something called an attention mechanism. Instead of reading sequentially, it looks at all the input tokens at the same time and mathematically decides which words are most relevant to each other, no matter how far apart they are.
Ah, so it can connect a pronoun in the last sentence back to a name in the first sentence.
Precisely. That's what lets it follow long arguments and keep track of a story.
But for it to do that, the words have to be numbers first. And if it's looking at everything at once, how does it know the order of the words?
Great question. So the first part is tokenization, turning the text into numbers. But you're right, that loses the sequence.
Dog bites man, and man bites dog would look the same.
It'd look identical to the model. So we add something called positional encoding. It's a kind of mathematical signature that gets added to each token's number, telling the model its exact position. You're the first word, you're the second, and so on. That gives it the order back.
This makes me think about what AI was like before LLMs. It was so fragmented. You had one system for translation, another for summarization.
A different one for chatbots, yeah. Each task needed its own purpose-built model.
So here's where it gets really interesting for me. How did LLMs change that? How did one model suddenly do all of those things?
It was a complete paradigm shift. And it was driven entirely by scale.
Scale.
Instead of training a model just to translate, we started training models on the general structure of language itself. We fed them so much diverse text that they learned the underlying patterns of reasoning, of facts, of communication that are embedded in how we write and speak.
So it learned language universally, not just for one task.
Exactly. And once a model does that, it turns out it can apply that general knowledge to many, many different tasks. Q&A, coding, analysis. It's all just language.
Which brings us back to that key word, large. When we say a large language model, what are we actually talking about? It's not just one thing.
No, it's really three key areas of scale. The first is the number of parameters.
Billions or now even trillions.
Right. And these are basically the internal knobs or values the model tunes during training. It's where the knowledge is stored. Second is the amount of data, which we've talked about.
And third,
the sheer amount of compute power. You need massive clusters of GPUs running in parallel for months just to train one of these things.
so what's the real difference then? Why couldn't smaller models do this? What actually happens when you cross that threshold, when you get large enough?
The smaller models were good mimics. They could capture surface-level patterns, the style of writing. But they would fall apart on anything that needed real reasoning or abstraction. They were great parrots.
But not great thinkers.
Exactly.
Yeah.
The scale enabled this qualitative shift, something we call emergent capabilities.
That's the key term. Tell us more about that.
Emergence is when a model, just by getting bigger, suddenly develops abilities it was never explicitly trained to have.
So it just starts doing new things.
Spontaneously. For example, a model might suddenly become very good at addition even though it was only trained to predict text. Or it might learn to translate between two languages it never saw paired together. It happens because the sheer capacity is finally there to connect all the disparate dots in the training data and form these higher-level concepts.
Okay, so that scale is the foundation. But a raw pre-trained model is not what we interact with. It can be kind of chaotic. How do we get from that giant probability machine to the helpful aligned assistant we use?
Right. That journey is absolutely critical. It's a multi-stage process. It all starts at stage 0. Randomly initialized LLM.
The blank slate.
Worse than a blank slate. It's pure noise. The outputs are just gibberish. It knows nothing.
Okay, so from chaos, we move to the first big, expensive step.
Stage 1, pre-training. This is where we feed it that gigantic text corpus. And its only job for months is to learn that one simple task. Predict the next token.
That's it?
That's it. And in doing so, it absorbs grammar, facts about the world, syntax, everything. But the result isn't a conversationalist. It just continues text. If you prompt it, it will just keep writing in the same style, often rambling on forever. It doesn't know how to answer you.
So stage 1 gives it the knowledge like a giant textbook, but stage 2 teaches it how to have a conversation.
That's a perfect way to put it. Stage 2 is instruction fine-tuning. Here, we stop the general training and use a much smaller, high-quality data set of human-labeled examples.
What did those look like?
They're instruction-response pairs.
Yeah.
So a question and a perfect answer. A command like, summarize this article, followed by a perfect summary. Thousands and thousands of these. This is what teaches the LLM to be an assistant, to follow a command and format a helpful reply.
Okay, so now it's knowledgeable and it's conversational, but it might not be safe or particularly aligned with what we want.
Correct. That's the crucial final step. Stage 3, preference fine-tuning, or PFT. Most people know this as RLHF.
Reinforcement learning with human feedback.
Exactly. And if you've ever been on a website where it shows you 2 responses and asks which one is better, A or B.
You were providing the data for this stage.
You were. You were creating human preference data. We use that data to train a totally separate model, a reward model, whose only job is to learn to predict which response a human would prefer.
And how does that reward model then change the main LLM?
Through a complex process, a type of reinforcement learning that basically acts like a continuous performance review. The LLM generates a response, the reward model scores it, and then the LLM's parameters are nudged in a direction that would have gotten a higher score. It slowly aligns the model to be more helpful, harmless, and honest.
Even for subjective things where there's no single right answer.
Especially for those. But then there's one more specialized stage.
For things that do have a right answer.
Correct. Stage 4, reasoning fine-tuning. For things like math, logic, or code, preference doesn't matter. Correctness does. Here, the model is rewarded only for getting the verifiable, factually correct answer. This really sharpens its ability to follow logical steps.
So we have this highly trained probability machine. Let's talk about the moment of generation. It's calculated the probabilities for the next token. How does it actually choose one?
It's all based on conditional probability. Given the context so far, what's the most likely next word? Now, the simple approach would be to just always pick the token with the highest probability.
Yeah, the most obvious one.
The most obvious one.
Yeah.
We call that the greedy strategy. And the results are, well, they're terrible.
Why?
Because it becomes incredibly repetitive. You get things like, the sky is blue, the blue is pretty, the pretty is nice. It just gets stuck in these high probability loops. It's useless.
So to make it useful, you have to introduce a little bit of controlled chaos.
Yeah, exactly. Instead of always picking the top choice, we use sampling. And the main control lever we have for that is called temperature.
Temperature, I love that analogy. How does it work?
So a low temperature, something close to 0, makes the model's choices very conservative and deterministic.
Right.
It will almost always pick the highest probability word. The output is predictable, factual, good for Q&A.
Okay, safe and boring.
Right. But if you turn the temperature up, say to 0.7 or 1.00, you're mathematically flattening the probability distribution. You're making the less likely words more likely to be chosen.
So you're increasing the randomness.
You're increasing the creativity and diversity. You're telling the model to explore the weird and wonderful parts of its knowledge, not just repeat the most obvious facts. This is what you want for brainstorming or writing a story.
That's a great explanation, but what if just dialing up the randomness is too messy? Are there more precise ways to control the pool of words it samples from?
Yes, absolutely. We have a couple of other key parameters. One is called top K. It's very simple. You just tell the model to only consider the top K most likely tokens. So if K is 10, it ignores everything but the 10 most probable next words.
That sounds a bit rigid, though. What if the 11th word is the perfect creative choice?
That's exactly its weakness, which is why many people prefer to use PopHep, also called nucleus sampling.
How is that different?
It's more adaptive. Instead of a fixed number K, you set a probability threshold, P, let's say 0.9. The model then looks at the smallest possible group of top tokens whose probabilities add up to 90%.
So if one word is super likely, the group is tiny. But if lots of words are sort of likely,
the group gets bigger. It intelligently creates a sampling pool that's wide when the path is uncertain and narrow when the path is obvious.
it's like a smart fence around the word choices. Okay, what about just making the text less robotic and repetitive?
For that, we have penalty controls. Frequency penalty discourages reusing the same tokens over and over. And presence penalty actively encourages using new unseen tokens. They both push for novelty and stop the model from getting stuck in a loop.
And lastly, how do you just get it to stop? To give you a clean, structured answer without adding extra chatter?
That's what stop sequences are for. You give it a list of tokens. It could be a period, a special word like end. And as soon as the model generates one of those, it just halts. It's essential for getting clean JSON or blocks of code.
Okay, so beyond these basic levers, the research is always moving. What are some of the more cutting-edge ways we're trying to make these models smarter or more accurate after all that initial training is done?
There are some really clever techniques emerging. One on the generation side is called contrastive search. This is designed to tackle repetition in really long generations, like an essay or a story.
Where things can easily start to sound the same.
Exactly. Instead of just sampling, it actively looks at potential next tokens and penalizes any that are too similar to what was just written. It tries to find a balance between fluency and diversity.
So it's actively trying not to repeat itself. What about the other big problem, factual accuracy, the model just making things up?
That leads to a really interesting idea called SLED. That stands for Self-Logis Evolution Decoding.
Okay, that's a mouthful. Break that down.
Sure. So a logit is basically the model's raw score for a token before it becomes a probability. Usually the model only listens to the logits from its very last final layer.
Right.
The problem is sometimes the correct factual signals exist in the deeper earlier layers, but they get watered down or corrupted by the time they reach the output.
So SLED is like the model double-checking its own work.
Precisely. It looks at the logits from all the internal layers and searches for a consensus. It's like an internal committee meeting. If the deep layers agree on a fact, SLED nudges the final output in that direction, which can dramatically improve factual accuracy without any new training. It's just using the knowledge it already has more wisely.
That's amazing. So optimizing what's already there. But what if you can't afford to build the biggest, smartest model? How do you get that intelligence into a smaller, cheaper one?
That's a process called knowledge distillation. It's basically having a big, smart teacher LLM train a smaller, more efficient student LLM.
How does that work? Does the student just copy the teacher's homework?
It's a bit more sophisticated than that. There are two main ways. The best way is soft label distillation. The teacher doesn't just give the final answer. It shares its entire thinking process, the full probability scores for every possible token.
It shows its work.
It shows all its work. The student is then trained to mimic that nuanced reasoning. It learns why the teacher made its choices.
But that must be a huge amount of data to transfer.
It is. It's memory intensive. So the faster, cheaper alternative is hard label distillation. Here, the student is only trained to match the teacher's final single chosen token.
Just the final grade, not the whole report card.
Exactly. It's less nuanced, but it still transfers a huge amount of knowledge and saves an enormous amount of compute.
Yeah.
So when you pull it all together, we've gone from a really simple idea, predict the next token, to this massively scaled, multi-stage, fine-tuned system. The magic isn't one algorithm. It's the emergent power that comes from stacking that scale, that architecture, and that meticulous human alignment, all on top of that one predictive function.
And that's really the synthesis for you. The power in these tools isn't some new kind of consciousness. It's the brute force of scale, the large, combined with the very careful, very human process of alignment and fine-tuning. It's engineering applied to probability.
Which leads to a final provocative thought. We know we align these models with human feedback and verifiable facts. But now it's becoming common practice to use the output of one LLM to train the next one via distillation.
Right.
So if an LLM is really just predicting what's most probable based on its training data, what are the long-term implications for knowledge itself if we start distilling these probabilistic truths into the next generation of foundational models? What happens when we start training our new models on what the last generation believed to be most probable?
A copy of a copy. Something to think about until our next deep dive. Thanks for joining us.